Welcome back to the lectures on Introduction to Multi-Agent Systems. In today's lecture, we'll introduce yet another feedback-based centrality measure, which is the hubs and authorities centrality measure. In today's lecture, to be a bit more specific, we'll again discuss what is the underlying logic behind the centrality measure and how exactly it was found. So let's get started. Around the same time, when the PageRank algorithm or centrality measure being developed, Professor Kleinberg, who's currently a faculty in the Department of Computer Science in Cornell, proposed the HITS algorithm in order to address the ranking problem of the web pages. What is HITS? Let's write the full form of HITS. So HITS refers to hyperlink induced text search. The HITS algorithm actually leads us to do two different kinds of central nodes in a network, referred to as hubs and authorities. So before we get to what hubs and authorities are, let's consider any general network. Perhaps any general social network or real world network. Let's put it this way. In general networks, there tend to be two kinds of influential agents, influential nodes, agents, or people, whatever be the context in which we are looking at. For example, there could be simply people who are very popular, let's say, popular nodes. Popular nodes could also be nodes which are highly relevant. In the sense of a web page, these are nodes which are highly relevant to the topic of discussion, to a given topic of discussion. Perhaps if we are talking about mobile phones, then a mobile phone manufacturer who could be a very popular node is, for example, Apple or Samsung or Nokia, like that. And then there are these other kind of influential nodes who are, we can say, followers of the popular nodes. Again, in the context of web pages, these could also be popular nodes, but not directly popular. We say Popular notes would give us information about give us information about the relevant notes for the given topic. We refer to the first kind of notes as authorities. And the second kind of notes, which are the followers of popular notes and give us information about them, are referred to as hubs in the network. So let us consider a small example to understand the notion of hubs and authorities. Consider a search, a query regarding the good phones to buy. Let us say if somebody enters this query online, goes to the web pages and is trying to find the good phones one can buy. Naturally, the first thought that comes are the good brands like, so let's write it. The authorities are nothing but the good brands that we know of, which are very popular. Apple, Nokia, Samsung, etc. And who are the hubs in this case? Now, for example, when you're about to buy a phone, what one does is generally they also talk to people around them, especially to the people who they trust and are sure that they'll get relevant and good information from them. So, friends, or relatives, or acquaintances give us, provide, or who direct us to a certain phone brand. Provide us relevant information about the authorities. These would be the hubs for us. So how does the hubs and post centrality, how does it work? Note that it is also quite similar to the PageRank centrality in the sense that both of them actually make use of the link structure of the web in order to discover the important nodes. However, they're also quite different in the sense that now, according to the HITS algorithm, we try to assign scores, two different scores to each node, which is a hub score, and the other one is the authority score. And both the scores lead us to the combined central nodes in the network. Yet another example would be places to travel to. In these cases, the authorities obviously have destinations, like, for example, one might want to travel to India, Australia, New Zealand, etc. Just to give an example. The hubs would simply be perhaps the influencers or the travel companies. Travel companies which direct us to different definitions. Destinations. Meaning, if there's a certain influencer who we follow, then whichever place they recommend us, more often than not, people tend to travel to those places. Meaning, when we are deciding which node is central or which authority is central, it is also important to look at how many important hubs are pointing towards it. Likewise, an influencer becomes more influential by pointing to the right set of authorities. In other words, we can say that a hub with a high score increases the authority score of the nodes or web pages it points to. This is how the score of an authority can increase if more and more hubs with high scores or more and more popular influences are pointing to it. Similarly, we can say the same thing about the scores of hubs. An authority with a high score increases the hub score of all of the hubs which point to it. All the nodes or web pages which point to it. Note that this is a very natural way in which a lot of decision making is generally done by people. So let us now try to understand how the underlying algorithm of the hubs and port centrality works. The underlying logic within it. The underlying algorithm is referred to as the HITS algorithm. To begin with, we try to identify the possible hubs and authorities in the network. Let's write it. The algorithm starts by identification of a subgraph of important nodes in the network. So this is in any large network, we try to filter out or consider only a subset of the nodes. And among this subset, we try to figure out which of the nodes are the authorities and which are the hubs. So what is the subgraph that we start with and how exactly we can calculate the subgraph? The answer to that, or one of the ways to do that, is the subgraph must contain the possible hubs and authorities. So how can we do that? One of the ways is to simply use a degree centrality measure, which will tell us the web page which has the maximum or highest occurrences of any given search phrase. One way is determine the nodes pages with maximum occurrences of the topic that we are searching about. Obviously, this method may or may not lead us to all of the hubs and authorities in the network. So in this case, we can do something else. We can extend the subgraph. Let's write it. The subgraph can be extended to consider all the other nodes or web pages which are connected to the set of the subgraph of important nodes. With maximum occurrences of the particular topic. So let me write here. Previously defined, meaning that we are referring to the same subgraph that we talked here. Meaning, if we define this subgraph as some S1, then here we get another subgraph S2, such that it is a bigger subset than S1. And what would it look like? Let's see. Let us now consider this very large network. Of these networks, only some of the nodes have been highlighted in green. So let us say these are the nodes which actually have the highest number of times that a certain topic is mentioned in them. Now, obviously, these green nodes may or may not include all of the hubs and authorities. So a simple way to increasing the size of the subgraph, because we also don't want to miss out on the important nodes, what we do is we also consider those nodes, for example, here, which have edges or which are connected to these nodes. We consider all of such nodes and construct our set S2, which is the subset in which we look for the hubs and authorities. So now let's try to understand how do we calculate or assign these hub and centrality scores to all of the nodes in S2. Thereafter, we assign a hub and an authority score to every node in the initial subgraph, in the initially chosen subgraph S2. By initially, we mean the subset chosen in the previous step. Now, as we said, that a good hub must increase the authority of the web page it points to, meaning a good hub passes on its importance to all of the web pages it points to. Similarly, a good authority must increase the hub score of all of the pages that point to it, meaning the authorities give their weights to the hubs that point to them. So how would we encode this information mathematically? Let's start. Let us define two vectors. Two vectors V defined as entries equal to V1 to Vn, where n is the number of nodes contained in S2. We define this V as the authority score. Highlight it. Authority score vector. Similarly, we define yet another vector U with entries U1 to Un, which is the hub score vector. Okay, now a simple rule that can do the job for us. What is the job? Again, to repeat, a good hub must increase the authority scores of all of the web pages that it points to. And similarly, a good authority must increase the hub scores of all of the web pages that point to it. Meaning, or let's write, for the ith node in the network, this information can be mathematically expressed as follows. The authority score Vi of the ith node is equal to the sum of the hub scores of all of the hubs that point to it, meaning Uj, it is the sum of all of the Ujs, where J is simply all of the in neighbors of node I. Similarly, the hub score of the ith node is equal to the summation of all of the authority scores of all of the nodes that it points to, meaning here K should be an out neighbor. So this is V of K. K should be an out neighbor of the node I. Obviously, if I points to a lot of important authorities, then its hub score increases. And if it is pointed to by a lot of important hubs, then again, its authority score increases. In the form of the matrix, let's write that concisely can be written as V is equal to A transpose times U, and U is equal to A times V. Please note that A here is the adjacency matrix of the subgraph S2 only. Let us now discuss an example to understand how do we compute these scores. Again, let's go back to the same example that we've been discussing in the past lecture as well, since the past few lectures. Again, we have 4 web pages here, 1 and 2 point to each other, and 3 points to both 1 and 2, and 4 points to only 2. Now in this case, let's assume that this itself is our subset S2. What would that mean? That would mean the following, that there's a possibility that there are certain other nodes in the network We've added a few more nodes in the network to highlight that the subgraph S2 is in fact, it only consists of the nodes, which we will highlight here. Nodes 1, 3, 2, and 4, and the induced subgraph, which is this. Let us assume that this itself is our S2. So how would we go about computing or assigning the hubs and hubs and authority scores to each of these nodes? Let's get started. Let's start by simply assigning the score 1 as the hub score and the authority score of all of the nodes. So this is just an initialization process. Now, the authority score of the first node is equal to the sum of the hub scores of all of the nodes that point to it. Meaning, for node number 1, the nodes that point to node number 1 are node 2 and node 3. And their hub scores are equal to 1. Summed up, the total score is equal to 2. Similarly, node number 2 is the nodes that point to node number 2 are 1, 3, and 4. In order to calculate its authority score, we add up the hub scores of each of these nodes. So this is a very simple example. This is a simple iteration in the sense that all of the hub scores are as of now equal to 1. Hence, added up, this value becomes equal to 3. Now, what happens to the authority scores of nodes 3 and 4? For node number 3, if you observe carefully, in the subgraph S2, none of the nodes actually point to node number 3, meaning its authority score is simply equal to 0, and the same happens for node number 4. Similarly, let's now calculate the hub scores. Now, the hub scores, or the hub score of the first node is equal to the sum of the authority scores of all of the nodes that 1 points to. So which are the nodes that node number 1 points to? It only points to node 2. And the authority score of node 2 is equal to 1 to begin with. Similarly, node number 2 points only to node number 1, hence the hub score of node number 1 is equal to 2, comes here. Let's look at node number 3. Now, node number 3 points to 2 different nodes. Nodes 1 and nodes 3. And what are the sum of their authority scores? That is equal to 2. Similarly, which node does 4 point to? It points to node number 2, which has an authority score of being equal to 1. So these are the Hobson authority scores in the first iteration. But remember that we need to normalize all of these values, meaning let us add up all of the authority scores. It's very easy to see that they add up to 5 in both the cases. In that case, after normalization, the scores are given as this. Now we can make successive iterations of the same process, and the stationary point at which all of them converge, or the stationary values of V and U, are simply the solutions of the Hits algorithm. Let's zoom in and observe what is happening in this case. As is intuitive, in this case, nodes 1 and 2 are the ones which have the only ones to have authority scores. Moreover, the authority score of node 3 is greater than that of node 1, which is also intuitive. Similarly, the hub score should be high, as we can see, of node number 3. And if you observe here, it indeed has a higher hub score. So this example illustrates us how we can calculate the Hobson, how we can assign the hub and authority values or scores to each of the nodes in a given network. This brings us to the end of the lecture. In the next lecture, we'll try to figure out in what cases can we get a stationary solution of this algorithm. Basically, the values of P and U, do they converge to certain values, certain fixed values? Okay, thank you.